today, Flex has been looking at applying blockchain in IoT technologies. We're looking at adopting that for our supply chain. We're also looking at, for our customers, how do you integrate blockchain into end IoT devices? And that's the theme of the talk today. And we'll talk some of the, this is the kind of the flow of the presentation. So I'm guessing everybody knows about blockchain. It is the underlying technology behind cryptocurrencies. Some of the graphics here show it rose in value in 2017 from about $20 billion to roughly $200 billion. It has taken a dip last year. It's still way above what its original valuation was 2017. And it's not just used in cryptocurrencies. It also has a lot of use in other areas, particularly supply chain, shipping and logistics. And one of the challenges in using blockchain in these other areas is how well the protocols scale into these lower cost IoT devices. And I'll speak to that in a few. In terms of blockchain's application and other use cases, I was looking at some of the venture capitalist report. There was roughly $1 billion invested in, VCs have invested in blockchain, non-crypto startups. So there's a lot of investment going in that direction as well. And we see that as well, and there's a lot of startups that have come and talked to us about that. So those are the areas that I spoke about. Shipping and logistics, the most well-known use case here is a partnership between IBM and Maersk. They announced a partnership to use blockchain to track shipments. Maersk handles about hundreds of millions of shipping containers moving across different ports, and they had challenges trying to integrate databases. In fact, there were paper records in some of these ports into one single location, and blockchain, due to its distributed nature, was able to build that trust to enable all of these entities to come together. So that's something IBM and Maersk has put out. Asset tracking is another area where blockchain lends itself very well. You can integrate blockchain's ledger technology to store the location of the assets as it moves through the supply chain. And the blockchain ledger itself is tamper-proof, so it provides itself very well for proving provenance of assets as they move through the supply chain. Food supply chain is an example. Walmart actually demonstrated something at CES called Food Trust, where you can have visibility and transparency into where the ingredients of your food, where they're coming from. Some of the use cases they were talking about was, if there's an E. coli issue in a lettuce shipment from particular farm in some place, blockchain will allow them to kind of track that and quickly in real time know which shipment or which farm had that E. coli impact. So those are some of the use cases there. This is, I actually threw the slide today morning. This is the demonstration that we did at CES in Flex. We demonstrated how you can use blockchain to track a drug supply chain. The premise here is you have a drug that goes from a supplier to the manufacturer to the wholesaler and right up to the patient. And if you speak to the IBMs of the world, they can help you put together that solution, having enterprise systems that connect up to all these different entities. At Flex, what we wanted to show is it's not enough that you track the drug up to the patient, to deliver it to the patient, but you also need to know when that drug was delivered to the patient. And that implies you need some amount of integration to the injectable or the patient drug delivery smart injector that the patient has. And that's what we demonstrated. The graphic here shows a drug delivery device that we built for a customer, and we've integrated that into blockchain. So that's we were able to run blockchain on a $10 to $20 microprocessor, and that was kind of the premise. So in this case, we use Ethereum, and I'll speak a little bit about some of the technologies in blockchain later. But we use Ethereum and smart contracts to store dosage of the drug onto the Ethereum network. And it's really, and if you look closely at the drug, you see fentanyl put on there, and my marketing team was all like, Anoop, do you really want to put fentanyl in there? Is that the right message you want to communicate across? But the real message I want to talk about was, there was actually, for the opioid crisis, one of the data points was there were 20 million prescriptions of a painkiller that went into one small town in Washington, and FDA had no visibility. That roughly translated to about 6,000 prescriptions per individual, and nobody thought anything was wrong, but FDA, who's supposed to be overseeing this, had no visibility there. So technologies like this will allow you to track that kind of usage from the supplier right up to the usage at the patient. Slide. So another interesting thing blockchains introduce is this concept of smart contracts. Smart contracts are a way to run actual programs on the blockchain. Ethereum was the first blockchain to introduce that. What it enables for an IoT use case is it enables these self-running executables that on certain conditions will get triggered, execute, and perform an action, which enables for IoT devices machine-to-machine communication. So machines can now communicate with other machines, triggering smart contracts to run, moving value from one bin to the other. So smart contracts is one of the key innovations that help in IoT as well. An example to quote here is, let's assume you had blockchain integrated to the fuel station in your, autonomous car drives into that and fills up fuel, or maybe it could be an electric charging station as well, charges electricity, and the smart contract would run automatically once the fuel or the charge has been completed, moving funds from the car owner to the gas pump owner. And smart contracts enable those kind of automate microtransactions to run. So quickly, state of IoT. For people who have been tracking IoT, when the whole term IoT originally came out, it was about intelligent things interacting with each other, and it's not just collecting data, but also acting on it, performing actions for the user. But the way it has evolved into is architecturally, IoT devices have become really consumer devices in your home collecting sensors, data, and pushing it back to the cloud. Not a lot of devices act on the data at the edge, but the data is pushed back to the cloud, and then you have front-end mobile phones or tablets or whatever pulling the data and presenting back to the user. That kind of architecture is really not scalable. One of the studies showed, by 2025, the average person will generate about 1.5 GB of data every day. So now sending all of that data back across to the cloud, acting on it, there's too much latency. You lose value for the data because you lose the context in which the data was generated. So this particular model itself is not something that will scale. True M2M, to truly unlock the value of IoT data, you need to consume the data at the end itself. So you need, maybe it's a door sensor that automatically communicates to your alarm and triggers when the door is open, rather than going back up to the cloud and coming. For that to happen, there are some closed ecosystems that enable that, but you need to have some amount of standard security frameworks that allow two devices to communicate to each other. And that's where we feel IoT may have a say in trying to standardize that. So it's M2M. So some of the challenges, and I think I just talked about, IoT has still continues to suffer from what's called the basket of remotes. In every IoT device, they these days come with their own user app. So that's as remote. So you end up with it's like the living room table. You end up with all these remotes for different devices on your home, and trying to integrate each of them is a pain. So that's happened to the IoT as well. It continues to have different applications controlling it. There's truly no single IoT. There's been several attempts, but nothing has taken off in that area. So the other problem is kind of related, but there is no single IoT framework merging these devices together for M2M operation. If you look at Bluetooth, there's pairing mechanism. Even then, it's still a manual pairing mechanism. It doesn't really work well out of the box. So that's another issue. Device identity is also a challenge. Bluetooth uses UUID. If it's a Wi-Fi device, IP address works, but even on the device side, it's not always clear how you identify the device. When we build devices for our customers, there's varying needs. Some of them use serial numbers, some of them try to put certificates on there, but there is no common standard. And it's a challenge actually for the cloud vendors. All of these devices sending data to the cloud, the Amazons and the Googles, they want to know who is connecting to them because they're being charged on computing and data usage. And that's one of the challenges they're having as well, because they want to identify the other side of the link as well. And finally, tamper-proofing, data stored in IoT devices, all kinds of privacy issues with that. There's really no, medical devices have a framework called HIPAA. Again, that's a set of rules. It's not really an implementation specification. So data is also out in the open. People can read it. There needs to be some standard framework to prevent tampering of that. So what is, what do you mean by a blockchain security? What are some of the layers? And there's lots of different blockchain technologies out there. I've tried to abstract it into a standard model. If you look at some of the common elements, the physical layer is the end nodes, it's mining devices, it's PCs, it's wallets, where the blockchain nodes run. On the network side, what are the protocols that use to communicate? Typically IP, the peer-to-peer network formation. There's also, I put PKI also part of it because PKI generates the keys that are used to identify the devices. That's also forms part of the network layer. The protocol layer is where the consensus algorithms, these are the algorithms used to update the ledger in a trusted manner. That's part of the protocol layer, the management layer to maintain the distributed database across nodes. It's also part of the protocol layer. So if you look through some literature, you will see protocol layer, some protocol or ecosystems for blockchain like to split the protocol layer into a layer 1, layer 2 within it as well. They call the layer 1 a base layer, which makes an interoperable protocol to communicate for that ecosystem. And then there's a layer 2, which adds extra features without breaking the interoperability. So some ecosystems will split up protocol layer into a L1, L2 as well. And finally, there is the application layer. This is where you run the applications on top of the blockchain. The term they use now are dApps, or distributed applications. The SDKs are part of the applications. The wallet management software, they're also part of that application layer. So again, this is one way to look at it. It's still the blockchain technology is still evolving rapidly, but I found it very useful kind of segmented into four different layers. So what are some of the key technology areas inside the blockchain? Fundamentally, the cryptography functions are public key infrastructure crypto functions. It uses nodes that use a key pair to identify the nodes. In fact, the blockchain node uses a hash of the public key as its identifier. And then it uses hashing to make sure that the transactions are stored in a tamper-proof way, SHA-256. Now, the way the transactions are stored, it needs to ensure that the entire ledger is tamper-proof. And so, Bitcoins usually, every transaction has a hash, including the current and the previous transaction. That's kind of keeps the history in a tamper-proof way as well. There are some data structures used to simplify the validation of that. Merkle tree is one that Bitcoins use. Lastly, it's the consensus algorithm. So in a distributed environment, you have all these anonymous stranger devices coming together. You need some kind of protocol to ensure that the ledgers are updated in a trusted manner. And those various different consensus algorithms, Bitcoins use what's called proof of work. It's truly not scalable for low compute devices, so other protocols like proof of stake and others being, and I'll speak a little about that in the next few slides as well. So as we're talking about blockchain, just want to give a quick overview of the operation, and then we'll talk about some of the challenges in scaling blockchain into IoT devices. The typical blockchain network is a peer-to-peer network of nodes. It consists of a distributed ledger. The simplest model is the ledger is duplicated in every node. The ledger is arranged as a chain of blocks, and that's where the term blockchain comes out, each block contains a set of transactions. So whenever there is a transaction from one node to another, the peer that generates a transaction adds it to a pending block of transactions. And finally, one of the nodes or multiples of the nodes on the network, in the case of Bitcoin, they will pick up this chain of pending transactions, will perform a consensus algorithm, and will add that back to the final main ledger. And that process in the Bitcoin case is mining, and the node which succeeds in adding it back to the ledger will be rewarded with certain currency. So that's how it works in Bitcoin. The mechanisms are different for others. I just want to take Bitcoin as an example. The final verified transaction then added to this. This is the kind of a standard sequence of flow for every blockchain. The mechanisms, the protocols may change a little bit, but the flow is pretty standard. So now, one of the challenges with moving an operational sequence like this to IoT devices are much more in scale. There's millions of IoT devices. They could be generating thousands of transactions per second. So a standard blockchain protocol that works for cryptocurrencies may not always scale well. And let's look at what some of those factors are. So the three key aspects that affect scaling challenges are transaction speed. This refers to how many transactions can you generate per second for any cryptocurrency. The second one is computation power. I spoke about proof of work being one type of validating ledger updates, but proof of work is highly compute intensive. So that's one challenge. And finally, storage. So if you're storing a ledger with all of your history of transaction, you can only imagine how big that can be, and trying to copy that in every node probably won't work for IoT devices. You need some innovation in that area. So let's now look at what each of these mean. So this is a graphic that shows the transaction speed for different kinds of technology. You can see Visa or credit card companies, they're built to handle up to 24,000 transactions per second. Bitcoin, on the other, can only handle about 7 transactions per second. So that's one of the reasons you want to, if somebody who's used Bitcoin or purchased anything, you will know it takes a few hours before your account is updated with the transaction. And there are other Bitcoin protocols. Bitcoin Cash is a fork of Bitcoin that optimize the transaction speed. It can do about 60 transactions per second. Ripple on there shows 1,500. Is another version of blockchain that's created by some of the banks, and it's a Chase, and a bunch of banks built a consortium to build that. So Ripple is built for fast transaction as well. It does about 1,500 transactions per second. Some of the things that affect transaction rates are block size. So remember I told you pending transactions are put into a block, and then the block is being validated and added back to the final ledger. So so it makes sense that the block size would affect the number of transactions that you can add. But the trade-off being, if you increase the size of the blocks, then now you're looking at larger traffic and larger storage requirements. So there's a fine trade-off to be built in trying to figure out the block size. I believe Bitcoin block size was about 1 MB, and I think Bitcoin Cash, when they forked it, it moved to about 32 MB, and I don't remember the exact numbers, but that's why Bitcoin Cash has a higher transaction speed. The second one is what kind of computational algorithms you use for your consensus. So proof of work, I was telling you earlier, is pretty computation intensive. You can choose lower footprint consensus algorithms, but then you're trading off some amount of security when you do that. And then finally, hashing speed. This is more a function of your hardware, how many hashes, because hashing is the fundamental way you're validating the transactions. You want to use a hardware architecture that can perform SHA-256 hashes really, really fast. If you look at some of the FPGAs that some of these mining companies are building, their hardware architectures are optimized for doing thousands of simultaneous hashing. That's what the mining computers basically are. All right, so those talk about transaction speed. These are some of the different ways the transaction speed has been optimized in existing blockchains. Fundamentally, there are two ways they optimize a protocol. One is off-chain networks. off-chain implies is you don't actually add the transactions to the main chain. Remember I was talking about when there's a transaction, it's added to a block, and then a node would validate the block before being added to the main chain. In off-chain, you keep adding it to a side chain, which is not the main ledger, and then at other periodic intervals. So you basically create a depth of transaction, and then periodic intervals, you have an algorithm that runs and merges the off-chain back into the main chain. Lightning networks is one version of the off-chain. Plasma, another version. In Plasma, what they did was Lightning networks, the off-chain is only transient. Once you finish validating, it's added back to the main chain. In the case of Plasma, the off-chains remain there. You only just add a hash of those the side chain back to the main chain. So, by the way, I use off-chain and side chain, but it's the same. They use different names for that, off-chain or side chain. The challenge with retaining the side chains in the case of Plasma is you typically want the nodes in there to have some notion of trust. So again, it's all a trade-off when you build a network. How resilient you want the systems to be. Lastly, there are newer technologies coming out. They don't necessarily use the same block data structures. They use something called DAGs. IOTA is very famous here. They're actually targeting M2M IoT devices. And it's still early days, and there's a lot of debate on, what that really is. That really secure? Is that open to 51% tax? So, but just want to capture here for completeness. That's also being investigated. Computational power. Fundamentally, what the computational power is trying to solve is making sure the distributed ledger is updated in a trusted manner. The problem, the terminology they use is the double spend problem. So primarily what it means is, in the end, your transactions are stored in a ledger. What if somebody just copies that, the currency moved over and starts using it for another one? So to prevent that duplication of the same you got to have some validation whenever it's added. So all of the consensus algorithms start trying to primarily solve the double spend problem. Proof of work was the original Bitcoin's algorithm. It came from research that was looking at economic incentives to avoid denial of service operations. That's why it's a very compute-intensive operation. What Bitcoin really does is it has every node to generate a hash with certain number of 32 leading zeros. They're all spinning out there trying to meet that requirement, and finally the one that wins gets to add it back to the transaction, and he gets paid with certain resource that's called mining. So we spoke about that, and let's go to the next slide, just kind of see what all. So we spoke about proof of work. It's slow, it's high energy, a lot of computation. You have to have the concept of a miner in this case, because that's how you compensate the nodes that go through this brute force calculation. There are other algorithms called proof of stake. And Ethereum has a proof of stake variant. In the proof of stake, it's truly not mining, because the blockchain system, you will not create any new currencies. It starts off with a certain fixed set of tokens. And any node that's wanting to validate the transaction needs to put up a certain amount of deposit or stake. So all currencies are created at the beginning. It is fast, it's lower energy, unlike proof of work. And when the entities that validate these transactions, they're called forgers, and when the forgers completed, they're paid off a certain percentage of the transaction. So let's say you want, you generated a transaction between A to B for 1,000 Ethereum tokens, you would pass off maybe 1% of that token to the nodes that's doing the validation. So in Ethereum, it's also called gas. So those are some of the things you need to consider when you're using Ethereum. You got to be very careful when running smart contracts, because the larger and more expensive the smart contract, it consumes more gas, and more you need to pass that back to the forgers. Last one, there's some new protocols called PBFT, Practical Byzantine Fault Tolerance. It's not necessarily, it's almost like a polling technique with some protocols on it. It's fast, but at this point, it's not really clear how well it scales for large amount of nodes, but there's a lot of investigation and research going into those kind of networks as well. Let's see. Storage, so if it's a large ledger, Bitcoin, the ledger size is about 200 GB. Trying to store that in every node, of course, doesn't practically make sense, especially for IoT devices. There's a lot of different ways companies or blockchain ecosystems are looking at solving this. And let me just go to the next slide. And there's several different techniques, but two techniques I want to talk about here is one is a concept of lightweight nodes. So in fact, Bitcoin supports that. There are clients which don't need to store the entire ledger. They can just have the wallet and then they can execute the transactions. So those are called lightweight nodes. The challenge with this is they are dependent on other full nodes. So in a network with too many light nodes, you're not really getting the security. So that's again another trade-off that you want to consider with lightweight. The other technique called sharding is a technique that's very common in databases. You kind of scrape certain rows of the database and store it in different nodes. The challenge here is, connectivity. What if the node that has that particular shard goes down or is out of range? So you have to have some management algorithms going around and rearranging the shards or maybe making multiple clones of the shards. But those are two techniques that are looking. So I just want to mention also there's something called IPFS. It's an interplanetary file system. These are techniques to store large files on Bitcoin nodes, very similar to torrenting. It's basically hash lookup based content addressable data. So you have data that's stored on different nodes, but you use a hash of that data to index up which node has it and pick it up. So it's being used to build file systems on top. That's another technique you can also use to break up the ledger. So it's also, there's also a lot of innovations going on in that area. So we talked about what some of the challenges scaling blockchain into IoT devices are. Next set of slides, I'm just talking about what an ideal IoT device looks like. So imagine now you figure out what kind of blockchain protocol you want to run. You're building a supply chain asset tracking device, and what is that hardware architecture that looks like for tracking the asset, and how does it connect up to the blockchain? So the hardware architecture is very similar to existing wallets. If you've seen Ledger, Nano, there's some wallets available to store Bitcoin currency, and I'll talk about it a little bit. So you'll start off with an architecture that is used for wallets, and on top of that, you will add some hardware acceleration for hashing. There's actually newer silicon vendors that are coming up with blockchain-enabled SoCs as well. Now, we'll speak about that a little later. So this is the hardware architecture for Ledger, which is a Bitcoin wallet. And you can see, in general, it has a main processor where the applications run. It usually has another secure processor which actually stores the encryption keys and runs the core Bitcoin algorithms. And then there's a bunch of user input. And so this is now, I think, I don't recollect the exact price, but probably the market price is in the $50 to $40 range. But you're probably looking at a BOM cost of less than $10. So this is, I thought it was a very good example of trying to see how low can you go with, from a resource point of view on an IoT device. So with that, let me just go to the next slide. Yeah, so based on that previous architecture, what you would do is you'd have a general purpose MCU with what's called a secure enclave. There's various different terminologies. There's also secure elements. The secure enclave or secure element will still have the tamper-proof memory. And then you'll have hardware acceleration for hash and any kind of PKI functions. The secure enclave or a secure element is typically tamper-proof, as in nobody can take that chip out, take off the couple of first layers and read the memory out. As secure elements have metal grid arrays on it to prevent that kind of active probing. On the MCU side, you can store the application, but you still need some drivers to access the cryptographic function. So we use ARM's Cortex M23, M33 architecture quite a bit. ARM released this architecture last year to bring trusted execution to microcontrollers. So I'd recommend using an MC with that kind of ability to have a cordoned off area to run your trusted apps. That's where you'll host your algorithms and your drivers to interface to the secure enclave and the accelerators. From a crypto acceleration point of view, it's good to have hash acceleration. As we talked about, hashing is one of the key functions run to secure the transactions. You need some hardware acceleration for that, and some PKI hardware, so something that can do your TLS handshakes and also store the PKI keys. That's useful as well. All right. So there are, I saw 2 companies. There's a whole wide of other silicon vendors that build machines for mining. Here I'm just looking at chips that are used and the end node to run the actual protocol. So Skynet was one company that recently put out a paper around building blockchain SoC chips. There's 3 different versions of it. Fundamentally what they have is hash acceleration. They have some secure enclaves and trusted app partitioning. The other company is Filament. Flex is actually invested in Filament, so full disclosure here. But again, their idea is to build an architecture that allows you to run blockchain in smaller resource constraints. But similar philosophies, hash acceleration, secure enclave, and it's actually being used in some products already. And with that, let me wrap up my presentation. So we kind of walk through how blockchain technology can help with IoT. It can be used to enable machine-to-machine interoperability using smart contracts and such. It builds a kind of a standard secure framework around identity using PKI, tamper-proofing using hashing and distributed ledgers, and finally it enables distributed trust models based on its consensus algorithms. I talked about how smart contracts can be used to automate microtransactions between the nodes. And then we went into what are some of the challenges in scaling blockchain. We talked about transaction speed, computational cost, and finally storage. Those are 3 parameters. And we walked through several options here, and that's one of the first things to do when you are designing your IoT use case, kind of go through the options and figure out the right balance between scalability and security. Lastly, we also talked about some of the hardware architectures that can be used to run IoT in a low-cost environment. Here we looked at microcontrollers, the $1 to $2 MCU ranges, and how they can be used to run blockchain protocols. So just want to leave with you a parting thought. Blockchain technology is still in its early stages. It's kind of like where I'd say internet was in the 90s. It's still connecting up devices and bringing together these disparate devices. There continues to be a lot of innovation in the protocol area, and we feel blockchain could be the precursor to the next generation of Web 3.0, where we have distributed apps running in all kinds of devices interacting with each other. So we feel very positive about blockchain's future in the IoT space. We continue to look at investing in that and trying to scale it down to the cheapest devices.